Yes, thank you for organizing this conference. Thank you for asking me to give a talk. So I'm going to talk about learning determinantal point processes from moments and cycles. And this is a joint work with those three people. So actually, I think the sizes are right, because Ankur is quite tall, and John is a football player. He's quite big. Actually, he's very big and tall. Okay, but first of all, happy birthday. So I did the math, and actually I did math, thanks to Sasha in particular, and actually to Sasha squared, so Sasha Tsibakov and Sasha Goldenschluger. And when I actually started doing statistics, this is when I met Oleg, who, so I was visiting Sasha Goldenschluger in Haifa, and I saw, so Oleg visited for a week, and I saw this guy walking like that in a corridor for hours. And he was just thinking about problems. And so once I asked him, hi, I'm Victor, what are you doing? And he explained, like, for an hour, he took an hour just to explain to me what he was doing. And I think it was adaptation. Okay, so let me talk about DPPs. So DPPs, you may know some probabilistic models for dependent binary variables. For example, Ising models. So DPP is a class of probabilistic models that is a little bit like ferromagnetic Ising models, because they model negative dependencies between binary variables. So the thing is that unlike Ising models, they are tractable, so you can actually compute everything. And this is why they're very much used in integrable probability. Because, for example, when you want to compute marginals or conditional probabilities, you can actually compute everything with closed form formulas. So this is, I think, one of the main reasons why they're commonly or widely used in machine learning. And in addition, you can sample, so there were a few papers in the past few years that show that you can sample fast those probability distributions. And so they're widely applied in machine learning. So I give here a few applications. And actually, I think one of the first times they appeared, it was in quantum physics, and they were called fermionic processes, because they were actually used to model the state of energy of fermion particles that repel each other. And then, so here I just state a few applications. And also, actually, as I said, they're a tool that is very useful in integrable probability, and there is this reference by Borodin in 2011 that is, I think, a very nice reference that gives a review of what you can do with DPPs in probability. So I said that they're an alternative to Ising models, which are probability distributions on dependent random binary variables. But I will use another formalism. So actually, any collection of binary variables, like any binary vector, can be represented as a subset of n, bracket n, which is the set of integers between 1 and n. So if you have n binary vectors, you just take the sets of all the coordinates in your vector that correspond to 1. And this is how I will represent a binary vector, using a subset of this finite space of integers from 1 to capital N. So now to go to the definition, a DPP is a random subset. So again, corresponding actually to the location of the coordinates in your binary vector. But I will say that it's a random subset of this bracket n, which is this finite space of n items, labeled from 1 to n, where so the probability distribution corresponding to the DPP is characterized by those inclusion probabilities. So for any fixed j, that is a subset of your space, of your finite space, the probability that j appears in your random set y, the DPP y, has to be equal to the subdeterminant of some matrix, the subdeterminant where you keep the columns and the rows indexed by numbers in j. And K is a matrix that is of size n. N is the size of your space. it's a n by n matrix, and we assume that it's symmetric, and that all its eigenvalues are between 0 and 1. And actually, this is sufficient to show that these inclusion probabilities indeed define a probability distribution. Because, for example, it has to be that the subdeterminants of k are between 0 and 1, because you want those to be probabilities, and also they have to be non-increasing. So this is satisfied, you can see easily that this is satisfied when k is symmetric with all eigenvalues between 0 and 1. And actually, you can quite easily show that this is enough to ensure that you define indeed correctly a probability distribution on the set, on the collection of all subsets of this finite set. So, okay. For example, what is the probability that item 1 appears in your DPP? Well, it's equal by definition to, if you take j to be the singleton 1, it's equal to the subdeterminant of k corresponding to the singleton 1. So you just keep the first column and the first row of k, and you take the determinant, it gives you just k11. So the diagonal entries of k give you the probabilities for each item to be selected by your random set. And then if you look at j, for example, in the definition, j to be the doubleton 1, 2, well, the probability that 1, 2 both together are included or selected in your random sets is going to be this subdeterminant of size 2, corresponding to the first and second columns and rows of k, and this gives you this formula. And you already see this negative dependence here because, no. Okay, here. Because if you compute the determinant, you have the product of the diagonal entries that correspond to the probabilities of inclusion for each item separately, minus something squared by symmetry of the matrix. So this will be less or equal to the product of the probabilities. So it means that the probability for two items to be selected by your random set is less or equal to the probability to be selected if they were independent. So they are negatively correlated. And okay, and you can actually write from this definition, you can write the PMF of y, which is the probability for each j, for each fixed possible outcome, the probability that y is equal to this outcome, j. And you can show that if k has all its eigenvalues that are strictly less than 1, you can show by some algebra that this probability will also be not equal but proportional to to the subdeterminant of some matrix L, which is related to k through this formula. But I will not go into the details. But this representation using L, this parameterization, is actually the one that is mostly used in the applications. So if you read the literature in machine learning that uses those DPPs, you might actually see this L representation, and then they're called L ensembles instead of DPPs. But I will use K, the K parameterization in this talk. So, okay, that's just because I find it interesting, but it's actually not very useful in my talk and also in this work. But as you saw in this, the second to the last line, each pair of items is negatively correlated. So, which means if you look at your, instead of y, if you look at the binary vector representation, x1, x2, xn, that are binary random variables, each xi will be, xi and xj will be negatively correlated. The covariance will be negative. Well, actually, you have a property that is much stronger than that. It's called negative association. And okay, maybe I will not go too much into the details because I don't have too much time. But basically, if you compute the MGF, the moment generating function of the corresponding to the DPP, you will find such a formula, and you can show that it's real stable, meaning that whenever you have a root, so z is a vector of complex numbers, whenever you have a root, then all the imaginary parts have to be non-positive, and that implies that you have basically, instead of taking only two distinct elements, like 1 and 2, if you take a bunch of elements that are disjoint, then you apply any increasing function to those elements, and the covariance of the two new random variables that you get will be negative. So it's actually a property that is much stronger but there is a huge literature for, a huge literature. There is a very, let's say, a very interesting literature on this account, negative association. And for example, this is a paper that I really like that gives you plenty of consequences, for example, or other representations of negative association for binary random variables, random vectors. Okay, so what I'm going to talk to you about is the following. So now imagine that you observe n IID copies of a DPP, y1, y2, yn. So each yi is a random subset of your finite space. So you observe n of them. They have a random size. Each of them has a random size. But you assume that they all have the same distribution, which is DPP with the matrix K. Some matrix K that is unknown. And you want to estimate K. And so the approach that I'm going to talk about today is one of the approaches that you probably teach your students in Stats 101, or maybe Stats 102, let's say, the method of moments. So it will be quite simple conceptually. Okay, but the first problem is that K is not identifiable. As you can see, in the definition, if I go back to the definition, K appears only through its principal minors. So it's only the principal minors of K that are identifiable, but it doesn't necessarily mean that K itself, that you can recover just by knowing the principal minors, those subdeterminants of K. You might not actually be able to know K exactly. So two matrices K and K prime can give rise to the same DPP, to the same distribution if, again, they have the same principal minors, which actually is equivalent by a theorem from Oeding, for example, in 2011, to the fact that K prime can be obtained by pre- and post-multiplying K by some diagonal matrix with plus and minus ones on the diagonal, which is exactly the same as saying that K prime can be obtained by from K by selecting some columns and the corresponding rows of K and flipping their signs. And actually that will give you exactly the same principal minors. So then you say that two such matrices, K prime and K, are called D-similar. So D-similar, not dissimilar. They're D-similar. They're actually quite the same. And it means that we want to learn or estimate K up to this possible transform. So up to D-similarity. Okay, so method of moments. So it's actually quite straightforward, at least the first two steps. So again, you remember the diagonal entries of K are exactly the probability, the inclusion probabilities for individual items. So for example, remember K11 is the probability that 1 is selected by your random DPP. So, well, you estimate it by taking the empirical frequency in your sample. So you have a bunch of random sets, and you just count how many sets contain 1, or here, how many sets contain I. And this gives you an estimate of the diagonal entry of the ith diagonal entry of K. Then for the off-diagonal entries, well, just use the second formula when you take just J in the definition of the DPP, J of size 2. So you take two items I and J, and you remember the probability of I and J being selected by Y is equal to these 2 by 2 subdeterminants. So it means that you get Kij squared as something that you can estimate, the product of two diagonal entries, minus something that you can estimate using the law of large numbers, well, by taking the empirical frequency across your sample. And then it means that very easily you get an estimate of the square of Kij. Okay, now you want to know the sign of Kij. And this is actually where the most amount of work is. So, and the sign up to this dissimilarity, okay? Because you know that you can still flip the sign of some rows and columns and have the same DPP. So you want to estimate the signs, or let's actually rather say you want to estimate the sign pattern within your matrix K. So for that, okay, for the diagonal entries and for the squares of the off-diagonal entries, so far we have used the first and second order principal minors. So now the guess is that we'll probably use higher order principal minors. So you can estimate all of them. Of course, you don't want to, because there are 2 to the n of them. N, capital N, being the size of the problem. So you don't want to do this. But let's talk about a problem that is much simpler. Imagine that instead of giving you all estimates that you want of the principal minors of k, imagine that I give you the principal minors of k. I give you the whole list of principal minors of k. How do you recover k? So this is called the principal minor assignment problem. So imagine I have a k that I'm hiding from you, but I just give you the list of all its principal minors. All of them if you want. And I tell you, well, recover k. Tell me k. Up to, of course, up to this d similarity. Give me k, find k. So again, you can recover the diagonal entries and the off-diagonal entries up to the sign using in this list the principal minors of size 1 and 2. And then to recover the signs, well, you will want one thing that you can do is to define a graph that I will call the adjacency graph of k associated to k and use cycles in this graph. So I just on purpose, I want to sound a little mysterious. You will use cycles in the graph, but okay, let's define this. So the adjacency graph, which we also call the determinantal graph in the paper, is nothing but the graph on n vertices, so with no weights, no orientation, just a graph on n vertices where you connect any two vertices I and j if the corresponding entry in k is non-zero. So, okay, it doesn't depend on the actual value, on the magnitudes of the non-zero entries of k. So, for example, if k has this sparsity pattern, then the corresponding graph will be a path. Then in this case, in the graph, you will have a cycle. So then let me define the cycle space, or recall the definition of the cycle space. It's just a set of all cycles in a graph. So you have a graph, and here it's the adjacency graph of k, and you can define the space of all cycles. And in particular, I will actually be interested in induced cycles, which are cycles that have no chord. No chord, meaning, for example, here, you have, in this graph, you have 3 cycles, but only 2 of them are induced or chordless. Because if you look at the big cycle, it has a chord. In the middle, it has an extra link that connects two non-neighboring vertices. So, okay, those are induced cycles, and you can define, when you have 2 cycles, you can define their sum by just taking the symmetric difference of their edge sets. So for example, here you have 2 cycles, C1 and C2. If you take their sum, it just means that you remove the edge between them, the common edge. And it gives you this larger cycle, which as we saw is not induced because of this extra edge here. But you can define sum of cycles. And actually you can even put a linear structure on the cycle space with field that is GF2, the 0, 1 field. And on this field, on this linear space, sorry, you can define a cycle basis. So you can find cycle bases, which are just linear bases for the cycle space with this with the operations that we have defined. Okay, so if we go back to the principal minor assignment problem, now actually what you can see by just rewriting the formula that you have for the determinants. So if you look at the principal minors, so take one principal minor, you know it's the determinant of some matrix, some submatrix of K, and you know that you can write it as the sum over all permutations of J, of the signature of the permutation times K1 sigma 1, K2 sigma 2, etc. So you have this formula, the first formula that you probably learned regarding the determinants. And now you know that in each term, so for each permutation, you can actually write each permutation as a product of cycles. And then if you just think for 2 minutes, you realize that, okay, actually the determinant, you can write each such determinant as a function of the diagonal entries of K in the set J, the squares, or equivalently the absolute values of the off-diagonal entries in J, and the product of the entries of K along each cycle, each cycle in the graph of K, in the adjacency graph of K. So, okay, now if you want to solve the problem, well, you know now, again, you know the diagonal entries of k by taking the principal minors of size 1. You know the squares of the diagonal, the squares of the off-diagonal entries by taking the principal minors of size 2. And now you will find the cycle basis of induced cycles of G. So I will explain a little later how to find such a basis. But imagine that you have an algorithm that gives you a basis of the graph. And then you use this formula. So KC is a matrix of a cycle. So you take K, you restrict K to the cycle, to each cycle in your cycle basis. And you have this formula. And in this formula, you know everything. So you can write this determinant as a function of the diagonal entries and the squares of the off-diagonal entries, plus one last term that is just 2 times -1 to something, times the product of the entries along the cycle. So now, since you know this determinant, because it's in the list that I gave you, well, you know this product. And now, since you know this product, well, you know its sign. So now, for each cycle in your cycle basis, you know the sign of the product of the edges along this cycle. And now, you can solve a linear system in GF2 in order to find one possible assignment of the signs for each of the diagonal entry of K that will match with the product of the product of the signs along each cycle in your cycle basis. So this is a linear system in GF2. And actually, this will completely determine a solution of the principal minor assignment problem. So to summarize, you can find the diagonal entries of K. You can find the off-diagonal entries up to the sign by taking the principal minors of size 2. From that, you know exactly which entries are 0, which entries are not 0, because you know the magnitudes of all the entries of K. So you can construct the graph G. Then in the graph G, the adjacency graph of K, you can find, and I will explain how, but you can find a cycle basis made of induced cycles. Then for each cycle, you use the corresponding principal minor corresponding to this cycle, and you get this product, the product of the entries along the cycle, and then you find an assignment of signs along each for the off-diagonal entries of K that fits the product, the sign of the product that you got for each cycle in your basis. So okay, now let's go back to the actual learning problem. So now I don't give you the list of all principal minors. Now you have a noisy version of the principal minors, because now you can estimate all the principal minors by taking the empirical frequencies. So, okay, we will assume something, and we'll discuss that, but we'll assume that K is such that all the non-zero entries are bounded away from 0, or separated away from 0 by some alpha. So if you take an off-diagonal entry, it's either 0 or in absolute value is larger than some alpha. So, okay, now by using the principal minors of size 1 and 2, again, you estimate the diagonal entries and the off-diagonal entries up to the sign within the square root n rate. And then now you will already understand why you want the non-zero entries to be separated away from 0, because this adjacency graph, you want to have it, you want to recover it exactly. You want to know it, because then you want to find cycle basis of this graph. So this is why you want to assume that the non-zero entries of K cannot be arbitrarily small, because then it means that if n, well, if 1 over square root of n is smaller, significantly smaller than alpha, it means that by just thresholding, you're able to say with high probability exactly which entries of K are 0, which entries of K are non-zero. And then you recover, with high probability, you recover the graph, exactly the graph of K. Okay, then, and again, I will explain that later, how to do this, but you find the cycle basis of G, of your graph. And then, for each cycle in your graph, for each induced cycle in your basis, you estimate this principal minor. And well, since you can estimate this principal minor and the first term from the same formula that I showed a little earlier, you can estimate this first term. It's just a combination of the diagonal entries and the magnitudes of diagonal entries. And hence, you can estimate this product. Well, if you can estimate this product, hopefully, you can estimate its sign. Okay, the only problem is that because you remember, then you estimate this sign, you recover this sign, and then you solve a linear system to assign, to attribute signs to each of diagonal entry of k. The only problem of that is that you can estimate this product basically at the speed, more or less the speed 1 over square root of n, but it can be very small because in this cycle, any entry, so in this cycle, along this cycle, the entries of k are non-zero, of course, by definition. They're non-zero, but in absolute value, they can be as small as alpha. So if the cycle is very large, this can be very small in absolute value. It can be as small as plus or minus alpha to the length of c. But the problem is that you actually don't care about estimating the value of this. You want to estimate the sign of this. So you want this to be separated away from 0 as much as possible so that you can recover its sign with high probability. So this is why when you actually look for a cycle basis, you want to find a basis that has cycles that are not too large to ensure that those quantities will not be too small. So, and this is now how we find a basis, not any basis, but actually a minimal basis, by using this algorithm from Horton that was actually, it's a quite old algorithm, it's from the 80s, and it was revisited in, well, not so long ago actually. But it's an algorithm that finds in a polynomial time, well, here I give something more precise, but it finds, basically it finds a cycle basis with as small cycles as possible. And actually, if you can define a parameter L, which we call the cycle sparsity, and it's the length of the largest cycle that is needed in order to span the cycle space. And Horton's algorithm will find a cycle basis such that all the cycles in this basis have length that is at most L. So it means that now, for each cycle in your basis, this will never be smaller in absolute value than alpha to the L. And now, so this quantity, you can estimate it with at the rate 1 over square root of n, more or less, at the parametric rate. And so if 1 over square root of n is significantly smaller than alpha to the L, then you recover the sign for each cycle with high probability. So this is now the theorem. The theorem tells you that, well, if n is larger than this quantity, so let's recall the meaning of this quantity, you remember, to recover the graph with high probability, you want 1 over square root of n to be smaller, significantly smaller, than the magnitude, the worst magnitude of the entries. So you want 1 over square root of n to be less than alpha, meaning n to be greater or equal to 1 over alpha squared. Or let's say significantly greater. And also you will have log n because you have n squared entries, basically, for which you want to recover whether they are 0 or not. So we use a union bound and you will have this log n that appears. So this first term makes sense, and it comes from the fact that you want to recover which entries are not 0. And here the epsilon is the precision at which you want to recover their magnitudes. And the second term comes from the fact that, exactly as here, alpha to the L is the worst case value of this quantity whose you want to recover the sign. And you can recover this quantity with at the speed 1 over square root of n, more or less. So you want 1 over square root of n to be smaller than alpha to the L. And this is what appears here, with the constant 2, with a factor L here. And so this is the upper bound that we have for the sample complexity. So you need at least this amount of sample we show that if you have at least this amount of sample, then you can recover K, the kernel K, the matrix K, up to D similarity with precision epsilon. And we show that this rate is near optimal in a minimax sense, and near optimal because actually in the lower bound we don't have this L here, and we don't have this 2. We only have 1 over alpha, and I think that's it for the discrepancy between the upper and lower bounds. Okay, so let me conclude by saying that basically what we need we need two things to estimate K. We need to estimate three things: the magnitude of the off-diagonal entries. Well, the diagonal entries, the magnitude of the off-diagonal entries. So that takes time because you need to actually use all the principal numerators of size 1 and 2. You have basically n squared of them. Then capital N squared of them. Capital N is the size of the problem. Then you want to find the cycle basis of the graph that you have recovered with high probability. And to find such a cycle basis, and actually a minimal cycle basis. Minimal cycle basis again, which means that every cycle will not be too large in the basis, and actually every cycle will have length that is at most L, which is the cycle sparsity. And for that, you use Horton's algorithm that runs in a polynomial time in capital N, basically. And the rates that we prove are nearly optimal, up to some nearly optimal. And just one last thing that I haven't said, it's adaptive to L, because actually when you run Horton's algorithm, it finds a minimum cycle basis. It doesn't care about the value of L. You get L as an output of the algorithm. So it just finds, without knowing L, without knowing what is the largest, the largest length of a cycle that is needed to span the cycle space, it will find a minimum cycle basis. So it is adaptive to L. We don't need to know L. However, in order to recover the graph, the adjacency graph of K, we need to know alpha, because we threshold to know which entries, to know with high probability which off-diagonal entries are 0 or not 0, we threshold the estimators that we have. And basically we threshold them at the level alpha over 2. So we need to know alpha, and this is one defect of this. However, I want to say that here, you see that basically you can recover up to some terms that depend on the dimension capital N and L and alpha, but you can recover K up to dissimilarity at the parametric rate here. And this is only because we assume this separation away from 0 of the diagonal entries of K. However, you can prove that, and this is bad news, but you can prove that if you don't make this assumption here, if you don't make this assumption, if you just assume that K is any symmetric matrix that is symmetric and with eigenvalues between 0 and 1, then you can prove that the minimax rate for estimation is at least this. So capital N is the dimension. The matrix K that you want to estimate is capital N by capital N, and this will be the minimax. This will be a lower bound on the minimax rates for the estimation of K without such an assumption. But as of now, I don't know how to prove an upper bound, because the problem is that if you don't have such an assumption, you cannot recover G, you cannot recover the graph G, and then you have to use some other machinery to find the signs, basically. That's it. Thank you for your attention.
Are there any questions? Yes, so we're going to use the microphone.
Just a simple one. Why does it work if in your algorithm you replace alpha by square root of log n over n?
Oh, so yes, indeed. The thing is that here I could actually adapt to alpha by just thresholding at 1 over log n. And when n is large enough, this will work. The only problem is that I will have this alpha. Instead of having alpha, I will have something that explodes. But it will be logarithmic, so it doesn't really matter. So it would work indeed. But this will not give me anything minimax, though. Because if I threshold at 1 over log n, well, there might be, if I want something if I want to assume that k can be entries that are arbitrarily small, then one entry could be 1 over 2 log n. So then that will not work. But indeed, I can adapt to alpha. And
there's a question here.
Is there a simple intuitive way to understand this the sparsity parameter L is related to if basically you give me the graph with the adjacency matrix, can I look at its topology and say what L is, or do I need to run this algorithm?
Well, if the graph is dense, it will be 3. I think in general, the best would be to run this algorithm. If you want to find L, I don't know, there might be some algorithms that find L, but we didn't. The parameter L, we had to give it a name, the cycle sparsity, but because we didn't find anything about this parameter, about this largest length needed to span the whole cycle space, we didn't find it anywhere. So I believe there are no algorithms actually that output L, just L. So now the only thing that I would be able to do is to run Horton's algorithm, and then to look at the largest cycle in the output. But yeah.
Can you also remind what is the degree of identifiability? So you said in the beginning that you identify up to something.
Yes. So the thing is that K is identified only up to a flip of the columns and the rows. Okay. But in particular, so K is identifiable up to such a transform. Okay. So in particular, if K is diagonal, then it's completely identified. If K is diagonal, then dkd is equal to K all the time. And actually, you can show that actually the number of solutions of the principal minor assignment problem is exactly 2 to the n minus p, where p is the number of blocks of K when K is block diagonal. So it's actually, p would be the number of connected components of G, of the graph, the adjacency graph of K. So if K is connected, completely connected, then it's 2 to the n minus 1. If K is the identity, then the graph has exactly n connected components, and that will be 1.
All right, so let's thank